So welcome back. It is with my great pleasure that I introduce to you Professor Antonio Bicchi from the University of Pisa and the Italian Institute of Technology, who will talk about understanding, designing, and controlling natural motion. He will talk in place of Nikos Tsagarakis, who unfortunately couldn't be here because he had a very important deadline for his current project. He is building a robot who hopefully will participate to the DARPA Robotic Challenge, and that's why he couldn't be here. This robot is based on the principle of natural motion, so it's very important that he does this work at his best. So once again, welcome to Antonio Bicchi.
Good morning, everybody. It's a pleasure to be here. I'm sorry I missed the first few days of the school. By the same reason, I was working with Nikos and others for this deadline that we have for the DARPA challenge. And as Giorgio said, this is not irrelevant, so it is relevant to this bigger project. So today I'll speak about quite a few things. I have many slides, but some of them you have seen already, so I will go quickly through them. And of course, all the work that we report is not my own only. It's joined with other students and collaborators, and namely Arasha Giudani, Alessandro Altobelli, Matteo Bianchi, Manuel Catalano, who is here, and others that are listed here. So, again, some of these slides you probably have seen already, but you will tell me if I get into many details on something that you all know already. So, of course, we are all concerned about doing robots for interaction with humans. That will be applied in cooperative manipulation tasks, domestic applications, domotics, entertainment, assistance, rehabilitation, teleoperation, human augmentation. There are so many applications that require a robot to be in contact with a human. Now, most of us think that this will be the real big market for robotics, the real big driver for robotics in the years to come, and not the old paradigm of industrial robots. So the problem is how to make robots that are soft for interaction, yet strong, simple, but also dexterous, intelligent, and practical. So the idea that motivates us in the research, the beginning of this community of natural motion, is also linked to studying intelligence, not just mechanics, but also intelligence, a more ambitious program, through its embodiment. Means intelligence is not just brain cells, intelligence is the whole body. So the body is actually, the whole body is the organ of cognition, and we will try to understand how the fact that we have a body and we have constraints due to a body, we have 2 arms and 2 legs, not 3, not 4, but this is a constraint. We have only 5 fingers, not 6. So we have constraints, but those constraints are not just limiting factors of how we are built or our muscle system or our skeleton system. These are not just limitations to how we for our functions. They're indeed defining the way we work. So the intelligence that we have, the way we know it, is the fruit, is the outcome of having this body. And here I like to cite Anaxagoras, the philosopher, who said that the humans are the most intelligent among animals because they have hands. Right? Not the other way around. Aristotle thought that we had hands because we were the most intelligent. But Anaxagoras had it right to me in the sense that the way we think is related to the way we move. We manipulate the environment, we touch objects, for instance, with the hand. A hand will be part of the talk today. And so how these constraints are organized is the term that sometimes is used in neuroscience, is synergies. So synergies are ways by which the complexity of the body is organized so that the brain can control in a simple way, such a complex mechanism as the human body. So one of the approaches that we follow in this philosophy is understanding by building, is trying to reproduce functionality by understanding the musculoskeletal system, the biomechanics, the sensory motor control, the perception, even the cognition at the highest levels, and then trying to recreate. It's like the boys, I mean, like kids. You tend to understand, you understand when you can build something that works the same way. And I think there is an interesting comment we can do here. You might know that in Europe, Europe has dedicated a very large amount of funding to two projects, flagship projects. One is the Graphene project, and the other one is the Human Brain project. So in this Human Brain project, they are trying to replicate the human brain, basically, computational model, huge computational model of the brain. That project, of course, will have respectable, but it is attracting a lot of criticism. And one of the criticism, in particular, one criticism that I have personally is when you think of replicating the brain to understand intelligence, right, where do you stop? So you start with the frontal, parietal, occipital parts of the brain, the cortex, of course, then you may want to go a little bit deeper for the emotional parts, the motor parts, the cerebellum. So you include those parts probably, right? And then if you go down, do you stop there or do you consider that the spine is part of your intelligence? I think the spine is part, right? Because the motor control is in the spine. And then from the spine, all the nerves. Where do you really stop if you want to simulate the brain? Nerves, afferents, and after all our muscles are full and skin are full of sensors and actuators, right? So they have to be in the model. So if you really want to do a model of the brain, you have to do a model of the whole body. And that's what I believe is important about studying the intelligence through its embodiment, not just restricting to looking at the brain as if it were a big computer, because it is not. So here comes this picture of Narcissus that looks at himself, that I take as a metaphor of humans looking at the artificial, at the robot, as the counterpart, to try and learn about themselves. Machine intelligence has made huge progresses. In Puma 560, you're too young probably to remember, but that was the standard robot in the 70s, 80s, even 90s. It had a 68K Motorola, 160 kiloflops. And today, the dumbest smartphone has 40,000 times more computational power. So machine intelligence really made huge strides forward. Machine motion, though, if you look back at the Puma, you had servo motors. And if you look now at robots, most robots in until 2010 or so, you still have servo motors. So machine motion didn't have the same advances that we have had in machine intelligence. Why is that? Well, you have seen this tens of times, I guess, because the muscles and the body counts. Yeah? So what makes a robot very fragile and difficult to use is the weakness that we don't have because of our muscle system. So what makes a muscle different from a motor? Motors are accurate and rigid, while motors and gears are brittle, while muscles are resilient. Muscles absorb energy and restitute it, consume little energy, and they are capable of smooth, gentle motion, but can also be strong and accurate. So that's the goal. When you think of machines that interact with humans, then the requirements are different. Accuracy might be less demanding. Safety is a must. So the old paradigm that you still learn in most of the textbooks is designed for accuracy and then try to control for safety. So you design a machine that is very accurate, therefore it's to be rigid, therefore heavy, and then you try to implement controls, sensors, sensory-based control to have safety in the interaction with humans. Active control to do that. But of course that is not the way we follow, and we rather think that we should design for safety and then control for accuracy. Compensate flexibility or compliance with control for gaining accuracy again. And you probably have seen this already. I'm not completely sure because I was not here, so I'm not sure about what material has been presented so far. But this I will make very short. This was an early work we did on variable stiffness and soft robots. Here is an example of how the combination of the link inertia and the rotor inertia that is amplified through the square of the gear ratio can impact a human during motion. So you imagine of having an impact at some velocity, maybe with some compliant covering. So what happens is that, of course, safety imposes a limit on the maximum speed. And inertia also does. So you have a curve here where if you want to reach some velocity, you have to decrease the inertia. Or if you have a higher inertia, then you have to decrease the speed in order to have some level of acceptable risk. Right? So this is sort of the standard picture that you have. This means that basically if you want to be very safe, you have to reduce the speed. Therefore, the robot will be very, very slow, not acceptable in many applications. So how can you go beyond this limitation? One possibility is to insert compliance between the rotor and the link. Then you decouple the rotor inertia from the link. This is a big part of the overall inertia because, again, you use the square root. You use the root, the square of the gear ratio. Therefore, it's a big part. And the impact is less if you use this variation. Now, inserting compliance, fixed compliance and possibly damping between the motor and the link is sometimes referred to as series elastic actuation. That is a name that you probably have seen already. So if you now try to see what is the minimum time, Giorgio, can you help me with the past part? So the safe brachistochrone has been seen already here? Yeah, okay. So we can go quickly through this. So the safe brachistochrone shows that basically you can improve the performance for a given safety limit, but you can do even more if you allow the stiffness to be varied in real time. And therefore you get even higher performance. So Giorgio, you will be in charge of making me this fast forward when I'm repeating arguments that they have seen already. Yeah? So motors and muscles. In the human body, each joint is actuated by at least 2 muscles, and the co-contraction of muscular groups allows for both soft and strong operation of the arms. Now, what is the motors? Yeah, okay. I guess you have seen this already. So, rigid actuation, torque-controlled actuation, series elastic actuators, and then variable stiffness actuators. And this is what we are talking about in this school. I can skip this part because I'm sure that Manolo showed this already. And let me get to. So this part of modeling has been seen, yeah.
Part from Manolo and part from Alessandro.
Okay. So if there are questions about this part, I'll be happy to go through that again with you. So this is the interesting point here is that with variable stiffness actuators, and specifically, for instance, the cubes that we are using, you can really mimic the behavior of a muscular system, where you replace the R and C commands by these, the commands that you have in the VSA, the average or reference position and the stiffness reference here. And even the behavior, the nonlinear behavior of the muscle can be copied pretty closely by designing these things, these motors. So that was what motivated the Natural Machine Motion Initiative that you are part of now, I hope. And then from the, and you probably already know what the philosophy was here, to move and search application by basically making it open, letting everybody use them, and crowdsource the exploration of new territories. Okay, so these parts you see. Okay, I think I will be okay, I think Manolo has already given the optimal control part. Yeah. I think I can give you instead. Yeah. I know. This part, yeah, I think I can. Then teleimpedance. Okay, so we will focus on teleimpedance and hence. Let me just motivate a little bit this part. Okay, so I now take for given that we all agree that variable impedance is good. Okay, I hope so. Not yet, right? I agree. Sometimes I wake up and I say, is it really useful? Oh, okay. It's an ongoing quest. The problem is how to use variable stiffness, right? So assume that now that we have decent motors or decent robot muscles to do this. Now, the question is, how do we use it? It's not obvious, right? In the human body, we do modulate our stiffness, but the way we do it is not always very easy to understand. One reason is that we don't really know. It is difficult to measure stiffness or impedance in the human body. We can do that only on some conditions, as we will see. So there are two possibilities. One is to understand how to use variable stiffness. One is to use optimal control. And optimal control basically means, okay, now I have this mechanism with variable stiffness, and I have a performance index. I try to use the stiffness that minimizes that index in time. That's one approach. And you have seen the safe brachistochrone, the maximization of the hitting velocity, or the motion on a limit cycle. That's one approach to understand. Now, optimal control, more generally, is useful in robotics. Let me just take a little general comment on optimal control. First of all, optimal control provides a control synthesis procedure for complex systems. So you have a complex system, you don't really know what to do with the control. You can try optimal control. It gives you a methodical way of designing a control synthesis. Optimal control also provides a principle basis to compare the performance of different system designs. And this was important in the first phase of the design of these variable stiffness actuators. In the following sense, assume that you have two different motors, One is rigid, and one has elasticity. Okay? And then you say, okay, so which one is better? Which is the best actuator possible? Then you say, okay, my goal is very simple, to go from A to B, right? Not hurting a person in the middle, like the safe brachistochrone story. Okay. But then, especially when it comes to the flexible robot, you might say, okay, I'm doing this using PD control. You use PD control, you get some performance. And then you compare with the rigid. And then someone comes and say, oh, yeah, maybe this is not good enough because the tuning of your PD is not the best. I can do better. And someone could come and say, no, let's do LQR or LTI, H infinity control. Why not? So what's the performance of this motor and actuation system? It depends on the controller. So one of the good things of optimal control is that this motor and hardware will never perform better than with an optimal control. So if you can solve the optimal control problem, then you know that you factorize the control out of the problem. So this mechanism can do this if you control it optimally. Now, oftentimes, the optimal control might not be viable a solution. I'm not saying that optimal control is what you do in real time. The safe brachistochrone or the heat maximization, all of them are open loop solutions. That means if you start exactly from this configuration and you want to go exactly to that configuration and you know exactly the model of your system, then that control will do the best job. But that will never be the case. Okay? So optimal control will only, in some cases, will provide you a reference motion that then you will follow in closed loop. But what is most important is not even that, because very often the optimal control has to be recomputed in real time, and that is too time demanding. So you will not really do optimal control. What you will do, what still optimal control gives you is this absolute measure of performance that allows you to compare this hardware with that hardware for an actuator. Okay? And that's very important. Another thing that the optimal control gives you is some understanding of how things go. So, for instance, you've seen in the safe brachistochrone that there is this sort of mantra, stiff and slow, fast and soft, right? So that comes from optimal control. You see that the stiffness and velocity switch. The switching function is opposite. So in most optimal trajectories, you want to be soft when you're fast. Now, the exact switching times have to be solved, and they have to be solved numerically in most cases. So this might not be possible to do in real time when you really move the robot and you have an unknown situation and say, okay, let's compute the safe brachistochrone. It might take too long to do that. But you know that a good motion will almost always be combining soft and fast, stiff and slow. And similar for the other policies. So this is, you distill some lessons out of optimal control, more than just taking the exact trajectory in some cases. And finally, there is this, the third great big advantage of optimal control, and the reason why we in the school we have insisted a little bit on this, is that it represents a language by which you can dialogue with between natural and artificial systems. Yeah? So this is what we call bio-aware robotics. When we do robotics, we have to know what happens in the natural system, not always to copy, not always to mimic, not always to be inspired, but to know. Yeah? And just compare, maybe to make a different solution, but to know how it works. Why is this important? Let me show. Because when you want to do an abstraction, and the embodied intelligence philosophy means that a large part of the functional capabilities of an organ are in the physical characteristics. So, what do I mean? I want to learn something from a human, right? And then I observe how the human does something. The way a human moves is made by his embodied intelligence, is depending on the hardware of the human, the muscles and the skeleton and everything else. Okay? So if I simply copy the human motion in a robot, I violate the very hypothesis, the fundamental tenet of embodied intelligence, because my body, the robot body, is different from the human body. So if I do exactly the same thing that the human do, I make a big mistake. Humans do the way they do because they have that body, and my robot will never have the same body. It's metal, can approximate, can look like, we can make efforts to, but it's not the same. So you shouldn't just work at the level of one-to-one mapping by copying what the human do, but you have to abstract to understand. Go to an upper level, understand what's the philosophy, and then apply the same philosophy to the robot. I think this is the correct approach. And now you have to abstract from nature and then understand and then bring back to robots. And optimal control seems exactly the tool that you need to do this very often, because it is an abstraction that does this. So here is what I just said. Right? What can we learn by observing body A that is relevant to body B? And this is the abstraction that I was. So natural and artificial movement science and technology can meet and share ideas on different levels, especially through optimal control. So, again, optimal control is not to, I think, that's my opinion, I think that the true role of optimal control is not to solve each and every specific problem, but try to understand. And there are two main ways to use optimal control. One is inverse optimal control, applied to natural movements, and one is direct optimal control, through either analytical or numerical techniques, and to distillate principles that apply to classes of tasks. Let me give you examples of this, some of them from the literature. So this is a paper by Monbauer, Lomond, and others in 2010. They show that a stereotype of locomotor trajectories could be interpreted as the result of application of an optimization index. So what was the experiment? They asked, Alain Berthoz was also another, they asked the person to move and go through a door, basically, in the room, starting from many different positions. So I'll mimic it here. So it's basically, I'm here, the door is there. I'm here. See, I'm here, and the door is there. So I walk, and I go here. Yeah. Then later on, I might be somewhere else. I might be here, and the door is there, and I do this. So they took all this data. So notice that when I want to go there, I don't do this. There are infinite paths that I can take. But there is a pattern in what normally humans do. So what Monbauer and others did in this paper is to try to understand what is the human doing when it moves in an environment. And of course, they got all this data. The point now is how you understand this data. Right? So how can I say? One naive approach would be, take many data, and when, big data, big database, when the robot will be in the same position, go get the trajectory and do the same. Okay. We tend to prefer to be a little bit more organized in our way of thinking. So what they did was, okay, let's see if there is a performance index that people are minimizing when moving. Yeah? Is there an optimal control that people are solving when moving? So what they did is this inverse optimal control. From the behavior, try to understand what is the optimal control, the performance index that is being optimized. Okay? So the way you do this technically is, there are several ways. One is that you hypothesize a particular type of performance index, and you have weights. And then you try to adapt the weights of the inverse optimal control so that it will fit most of the trajectories, right? Which is one way of looking at a learning problem, if you want. So through this, they confirmed that humans tend to adopt a non-holonomic behavior. It's a little bit like if you had wheels. Indeed, my motion was not very different from what I would do if I had wheels instead of legs. Rarely humans turn on the spot, but they can do that. They do that under some conditions on the visibility. So it's a bit more complicated than just unicycle motion. But that was important to understand. And indeed, this work was joined with Alain Berthoz, who is a neuroscientist in Collège de France. And that was showing that the shortest path to a target with limited field of view could be predicted by these trajectories. These trajectories are a variation. So I was saying now that these are unconstrained. Okay. Now, this is a variation, and this refers to when you go to somewhere and you have limits on your field of view. So that means that your field of view is not completely open. Why is that? Well, first of all, in our own case, we don't see on our back. Yeah? We have some field of view, some cone that we can look at. We can also turn the head, so we have a larger field of view, but we never can go in the back. And there are other cases, for instance, in robotics, where you have a camera that looks forward and cannot turn, or even if it turns, you have a limited field of view. So how does that affect? When you go somewhere, you also want to see where you're going. So the problem is now, how do you go optimally, maybe doing the shortest path, by keeping an object within your field of view, without losing the object? So that was a problem that was asked, and this is, for instance, a simple unicycle that has an asymmetric frontal sensor. And this is an example of direct optimal control. So from the inverse optimal control that I explained before, we are now moving to direct optimal control. Now we are asking, okay, now I have a model. I have this vehicle here, for instance, that can move in the plane, has some non-holonomic constraints, and has limits. And I wonder, what is the best path to go, shortest or fastest path to go, without missing the object? Now, direct optimal control means you write the performance index, you have the dynamics, you do your math. Basically, you apply Pontryagin, you do the analysis, you do the synthesis, or if the problem is too hard, you do numerical control. Okay? And you find solutions. Here is one solution. In this case, we were pretty lucky because we could find the analytical solution to this optimal path. It's interesting to see that the optimal path is made of concatenations of arcs, optimal arc or extremals, that are either straight lines or arcs of a logarithmic spiral. So the optimal paths are either straight, if you have the object in front of you, you just go, or if it is not directly there, then what you do is you keep the target at the extreme of your field of view and you move towards the target. If you do this, the trajectory that turns out to be resulting from this extremal is a logarithmic spiral arc. So you see those spiral arcs here that take the vehicle in shortest time to the goal. Here is the goal. Okay. This applies actually to every vehicle that has limited, that has a non-holonomic constraints. And non-holonomic constraints means that you have limits on the velocities that are not obvious in terms of positions. So for instance, you have wheels, you cannot move sideways. You can only move forward or turning around. This is a classical non-holonomic constraint. And this is what you have in unicycles or wheeled vehicles. Okay? But again, we are talking about dialoguing between the artificial and the natural systems. So it is interesting to see that in many natural environments, if you have winged or legged creatures, those rules do apply. So for instance, here is an example of a nurse shark and goldfish that has a limited field of view, vision. This is an underwater vehicle that has a very similar situation in artificial. Here is a falcon, a raptor whose vision system and trajectories are depicted there that are to track a target. Also, a raptor has to fly, and when you fly, you cannot move sideways. Right? You have to turn or go straight by flying. So you have non-holonomic constraints. And raptors have a limited field of view. Indeed, they have a pretty narrow field of view. Of course, they could turn their head, but when they are catching a prey, they won't turn the head because the air drag would be too high. So they want to keep the most aerodynamic configuration. So the head will be fixed. So they have a very narrow field of view, and they have to keep the prey in view while they fly. The prey, they cannot take the prey in front of them because they don't see in front of them, right? Because their eyes are on the side. So raptors have to fly looking at the prey that is on their side. And even butterflies or moths fly according to the same principle when they do around a light bulb. It was very interesting that after having solved this direct optimal control problem having logarithmic spirals, you go in the literature, natural literature, and you find that sharks, falcons, and moths all fly along logarithmic spirals. These are natural data, biometric data from all those species. So all those species do the same. This is what I mean by saying that optimal control is an abstraction that can help you, take the real inspiration from nature. Okay, with this, I think I will skip some parts because you have seen this already. On the actual application of optimal control to variable stiffness motors. So I have given the introduction to the optimal control part after the optimal control part. I hope you still... Oops, big mistake. Okay, so we say we have variable impedance. How do we use it? One possibility, optimal control. Enough with that. Another possibility, how do humans use variable impedance? Try to understand what they do and do it again. Now, so one obvious thing to do, first of all, is to try and understand how humans do that by doing human studies. We know that arm stiffness is adapted to tasks and force fields. So there is a lot of work by Neville Hogan, Mitsuo Cavato, and then Etienne Bourdet, Gomi, Franklin, Chadmer, many, who looked at the impedance of the arm in different motions. Have they seen some of this? Through Etienne, I think. Yeah, Etienne extendedly. Of course, the results look at the impedance in one configuration after several learning tasks. As I said before, it's not easy to measure stiffness. It is possible during a repetitive task, like what Etienne Bourdet did. But if you wanted to know what's the stiffness while I throw an object, how does the stiffness change while I throw the object? I don't think anybody is able today of giving you an answer. We don't really know, because it's too fast to be measured.
This was a question during last talk.
Oh, okay.
Of
Of?
Fabrizio about measuring.
Okay, okay, good. Does it make sense? So, this is not easy. We don't really know how to do that well enough as yet. So another possibility is, okay, let the human do it. It's not general an approach. The thing that I want to talk about is not general, and it makes sense in some applications where you basically need to replicate some skills at a distance. So we call this a teleoperation of impedance, or teleimpedance. So you know what teleoperation is about. Teleoperation consists of measuring motor control parameters in human and replicating in robots. So the typical application is that I have a master and I have a slave. My left arm is my slave. So I move the master and the slave follows. Right? Teleoperation is very old. It's interesting, is older than robotics. So the very first mechanical arms that were designed in the 50s or even in the 40s were arms for teleoperation, much before robots, especially for nuclear waste disposal or nuclear manipulation. Remote control of position is rather easy. You just measure one position and you copy in the controller. And here is an example. But position control is not enough when you have that the slave interacts with an environment. Right? So you move the master and the slave, and then you want to do something on the environment. I mean, until the slave is free, no problem. But then when you have to do anything on the environment, say, leave this object down, so you go down, and then the master will get in touch with the slave, will get in touch with the environment. At that point, forces will be generated. And even a very small error in the position of the master or in the model will make a very strong force to be generated at the contact. So when you have interaction with the environment, and very often you want to control the force on the environment, how do you do teleoperation? So one classical way is to do remote control with force feedback. Force feedback means that you measure the force on the slaves at the interaction. So you need sensors, force sensors, that's okay. And then you need to display this force to the operator, to apply to the master, through the master, some force to the operator, so that he feels the presence of this table, although the table is not really there. Okay? Now, this has problems. First of all, you have to build an exoskeleton to give you your arm forces. You have to apply some mechanical jig on your arm to give you forces, maybe a haptic interfaces or whatever. Sorry. No problem. And then you might have stability issues because of the transmission delays. So it is well known that you are closing a feedback loop between your input here, the sensing on the slave arm, and then actuation back on your input. So you have this loop, and within this loop you have delays due to communication, and these delays force you to keep the gains low, because otherwise the system will go unstable. And if the gains are very low, accuracy is very little, transparency is very low. Transparency means the feeling, how convincing is the feeling of contact. So idea was, okay, we now have the possibility of controlling impedance. Can we do remote impedance control using the arm position and impedance as references for the robot, and then use the local controllers that are very stable, have no delay, to make the robot track those plans. Is that clear? So when I do position, I have no problem of instability because I tell the position, the robot does. I have no feedback. No feedback, no problems. When I do force control, I need feedback, right? So I'm in trouble. So the idea of teleimpedance is I don't control force. I tell the robot what impedance I want him to have. I want it to have. When the human arm is soft, the robot should be soft. And when the human arm is stiff, the robot should be stiff. And when I'm stiff in one direction and soft in the other direction, I want the robot to be stiff in that direction and soft in the other direction. Okay? By doing this, I hope I can get away without controlling the force. Therefore, just sending a reference, pure feed-forward control of impedance. So the idea is that the operator moves the hand and adapts his impedance to solve the task based on visual information from the scene. So we have to sense the position and impedance on the master. We have to control them on the slave. And then we have to ask, is this useful or not? How do we measure impedance? So one way of measuring impedance, probably now the simplest and most accurate, is electromyography. Electromyographic signals correspond to muscle activation and are strongly correlated with muscle force. It's very easy to implant, not invasive, relatively cheap. They're much cheaper than exoskeletons. Common signal of choice for prosthesis, for instance. The signals are not perfect, they're noisy, they're not too stable, so you need some good processing. But there is quite some work on measuring joint torque and stiffness estimation from EMG. You can do that in using a model of the arm, which is not trivial because going from the forces measured at the muscles to the torques at the joint is a long way because you have all the joints that are not really kinematic joints, they're all rolling joints. And you have the tendons that are not a fixed radius, but they change in motion. So the model is complicated. Or you can try and do calibration, the right calibration of the EMG to stiffness mapping. So you can basically do an experiment that is the following. You measure the EMG on the human, and you ask the human to change his stiffness or her stiffness, while operating on a robot that is controlled in stiffness. So you get a manipulandum, that is an object that you hold in hand, and this is fixed to a robot. And the robot measures positions and forces, and then it perturbs you, and it measures your stiffness, while you measure also the EMG. And now you correlate the EMG readings to this, to the stiffness of the end effector. So it's basically a map that gives you this map T of Q is a map that depends on the configuration Q of the arm. F is the measurement from the EMGs, and tau is the torques at the joints, at the human joints. And of course, these are the measurements of torque that you get from the manipulandum, and sigma is the stiffness that you can imagine to be obtained as the derivative of the torque with respect to the angle Q. Now, there are different aspects. The electromyographic signals are related to muscle force and not to displacement. So, when you measure the EMG, you cannot measure the position. You are not measuring the position. Indeed, I can be completely relaxed, zero force here or here. So I would have the same EMG reading in different positions, right? So EMG do not measure force. They measure activation of a muscle. So basically measure force. So to measure the position from the master to the robot, I don't think it's a very good idea to use EMG because there are many other means of measuring position, such as, for instance, optical or inertial measurement units. So the idea is control the robot force. Well, this is the idea that I don't like. You could control the robot force, integrate the human arm dynamics to find position. You'll be using gravity compensating forces, and then forget it. This is too long away. Measuring the force to find a position, it's never worked with us. But then, as I said, just measure the position. There are very cheap inertial measurement units or more accurate optical measurement units. So we measure the master directly, and we control the position through those sensors with higher priority, and then we control impedance in the null space of position control inputs. Okay? So basically, we now control the position of the slave and control the impedance of the slave without altering the position command. Okay? So we can vary the slave control in the null space. That means all the controls that will not change the position. We use those controls to change the stiffness. Yeah. So this is the scheme that we are using. This again, T is the map from EMG to torques. What we do is we take a measurement from the EMG directly. We project them in the null space of this map T. That means that you get torques that will not affect the position. And here you have the position control loop that gives you the torques that are needed to get some positions. And you add something that is filtering out the component for actuation. So the torques in the arm are divided into subspaces. One is the subspace that controls the accelerations, the positions, and one is the control that doesn't change that and only changes the stiffness because of the co-contraction. Here is the setup. You can put EMGs on the muscles, measure them, get the position comments from markers, and get the co-contraction and stiffness from here. Put them put them in a controller, and then use them. First of all, we use that in a KUKA arm. In the KUKA arm, we are controlling the impedance through force control, through the classical impedance control that is implemented in the KUKA. But you can do the same, and we did the same with variable stiffness actuators, where you have the control of the stiffness that is directly at the physical level. Here are some experiments. Here you see on the right, you see the arm of Arasha Judani that is doing this very simple task. Is moving the arm. You get the position from these sensors on the wrist, and the robot is following that. At the beginning, it moves with very little stiffness. So the robot tracks with very little gain that position. At a certain point at the end, the person stiffens up the muscle, the arm. Then the robot gets the same impedance, so its position gains are basically increased, and it will press more. So observe this again. At the beginning, he's relaxed, he's moving. You see the robot has an environment as a sponge. So the sponge is enough to keep him away from the reference. But when he stiffens up, then the robot also stiffens up and gets over the obstacle. Is that clear? So it's a very, very simple idea, actually. Embarrassingly simple, but effective. Let me see if I have the videos here. Yeah. So here is a classical peg-in-hole example. Roboticists have always been obsessed with this peg-in-hole thing. I don't really know why. So you have a hole and a peg. The hole is tight, and you have to put the peg into the hole. If you make a little error in alignment, then you will have very high forces. It will jam in the hole and will not go down. If you are in the hole, you have to press with some definite force in the vertical direction, but you have to be careful not to go in the wrong direction with torques or displacements. So basically, you have to be compliant in this direction and strong and stiff in the vertical direction. So there are directions where you want to be stiff and directions where you want to be soft. So what happens if you do teleoperation without teleimpedance, and you have the arm that is controlled with high impedance? So as you see here, the Arash is moving the arm, is getting to the point where the robot touches, and then you have this interaction. This interaction has very high forces that you could see from the screen if it were not so small. So you have two high interaction forces. Here is with low impedance. What happens with low impedance is that you can, to all effects, you cannot get the hole here. You cannot get into the hole. If you have low impedance, you can find the hole because you adapt much better, but then you cannot press inside. And finally, here is the teleimpedance. I hope you can see this. So here, the human is moving around. He's relaxed now. He touches the environment. He's very relaxed, so forces are very low. You're not controlling the force, but you are controlling the impedance, so the arm is very soft. And then when you get to the hole, you force it down. So you squeeze, you co-contract your muscles, and you go down. When you are inside, as you could see here, let me show the final part of this again. No. Was this the pegging hole? Yeah. In the final part, you will see that it goes, then it co-contracts to press the peg inside, and then he relaxes. And when he relaxes, he moves the arm up, but the robot will not come because there is a high force. The hole is very tight. So to get the peg out of the hole, the operator has to contract again. And what is notable is that, of course, this goes through a calibration of the EMGs that, as we said before, you need to know this T matrix, this mapping, and you have to calibrate that experimentally. Turns out to be pretty robust. So I used it with the same calibration data than Arash. Now, between Arash's arm and my arm, there is a big difference. He plays tennis almost professionally. I'm absolutely not that good. So he has twice the arm that I have. And still worked with the same data. And what was remarkable when I tried it is that it's really convincing. You feel like it's like you feel the force. And when you abstract it, it seems to you that you are really feeling the effect of the disengagement from the hole. So it's interesting. Of course, it has limitation. You have to see the scene. You have to decide the stiffness depending on the phase of the task. It's the human that controls. But it is, one application that does away with all the need for force feedback, exoskeleton, stability issues, and so on and so forth. Another application for this is ball catching. So here the task is to catch a ball. Still have 50 minutes, right? Catching a ball. Now, catching a ball is a deceptively simple task. It's not really too easy. So the ball is coming down. Let me stop it a little bit. The ball is coming down, and what happens? If you are too stiff, the ball will bounce on the plate. If you are too soft, you will bow too far. You want to do something like the human does. The human does a motion that is like absorb a little energy and then restitute. And to do this, we apply some pattern of impedance. At the beginning, we are soft, and then we get stiffer to bring it back to the final position without going too far. So here is the experiment. Let me show from the beginning. Yeah, this is constant high endpoint stiffness profile. So the robot is controlled with constant stiffness, moves following the human. Oops. Yeah. And you see that the ball bounces quite a lot. Then it is controlled with soft impedance, and the robot will give much more than the human does. So this is low, constant low stiffness. You see that it yields much more than the human. And here is tail impedance. Now, in this last case, we are using the idea of measuring the EMG and replicating the same stiffness. And you see that the motion is very similar to the human. The position is still controlled by the human, so you see that the ball is going, the human controls the position to catch the ball. Okay, I think we can go quickly through this because we have seen this already. And these are some details on how you model the stiffness and how you practically estimate those mappings, but I think these are a little bit too much of detail. So next part. So this concludes the first part of the talk, and then I move to the second part, if you're still alive. And the next part is on hands. And it's again embodied intelligence approach to taming the complexity of hands. Again, big group. Yes?
Before we start with the next part. So,
okay, yes.
So, for my understanding, the most complicated part is that mapping, so finding matrix T. Mm-hmm. And how robust is that matrix? Because you said that for different subjects, I suppose it's very different. So from the very beginning, you have to measure EMG, which is very noisy, but also you have to calculate stiffness. And even for the same subject, when your skin gets wet, so I believe that these measurements are very different. So everything is.
Yeah, this was actually our assumption. We thought that it would be very, very fragile. Indeed, it is not. The same subject, for the same subject in the same position, is very stable. You can use data from yesterday or from weeks ago. This still works. Between subjects is surprisingly stable. as I showed before, I was using the system with my students, who is very much stronger than me, data, and it was still working. It depends on how accurate this is, but probably the calibration is not very accurate, but the teleimpedance works. Basically, when we do teleimpedance, we are controlling roughly. I mean, we don't need a very fine control of the impedance. So for the peg-in-hole task, it was working okay. I'm not able now to tell you how accurate that is between subjects. This is actually a study that we are trying to do now. What changes rather consistently is calibration in different postures. So if you calibrate in this posture and you want to use it in this posture, it will not be working. That is for sure, because the mappings are completely different. Now, either you use the model of the arm, which will make the dependence very strong probably on the subject, or you try to to calibrate in many different positions and then interpolate. This is ongoing work, so we haven't done that yet. So your point is, yes, you're right. It is depending on calibration, and it is in principle not very robust to changes. It works a bit better than what I would have expected, and probably connected to this, there is another point that is interesting. We have noticed that, I don't know if I have let me see if I have something to show you. I mean, experimental data of this. I thought I had them. Let me see, maybe they're hidden. No, they're not here. So, but I can explain it. I don't have the data. We were, through that inversion of this matrix, we were measuring the stiffness of the human arm in the X, Y, and Z directions, and then replicating the same stiffness on the robot arm on the X, Y, and Z direction. You can do that through the controller of the KUKA or with one of the cube systems that we have, right? After doing this, we did the tasks, and we recorded the stiffness and the variations along the tasks. And at the end of this, we submitted the paper to a journal, and the reviewer said, well, if you look at the stiffness in the three directions, they're varying during the task, but they're very strongly correlated to each other. So the three of them, X, Y, and Z, always changed in a very similar pattern. And his question was, so why do you use three? So it seems from our data that when you control the human arm, you don't really do X, Y, and Z. You don't really control them independently. Well, our answer to the reviewer was that, yes, now we know, but we didn't know at the beginning. So this is a new result. But after that, we actually started investigating why is that so. It seems, this is preliminary data, so it's open for contribution here. It seems that humans do not really control the impedance in different directions, like we are used to do in robotics, for instance, for the peg in the hole. So classical wisdom in robotics is that in peg in the hole, you want to control high stiffness in the vertical direction and low stiffness in the rotational and lateral directions, right? This is what you learn from books, right? It seems that humans do not do that. Indeed, what they would do, what we observe is that humans are compliant in all directions before contact, and once the contact is established and they want to press, then they become stiff in all directions. So it is more like the humans are either soft or stiff in all directions at the same time. So the question is, how do you really adapt to different directions? again, what we observe is that humans use the posture of the arm to change the directionality of the stiffness ellipsoid. So when you want to, I move a little bit. When you want to press something in this direction, you put your arm in this configuration. You don't do this. Right? So if you want to be very stiff in this direction, you do this with the arm aligned. So the configuration controls, thank you. The configuration controls the stiffness directionality much more than the co-contraction. Co-contraction does not seem to be directional. It's simply higher or lower stiffness in all directions. It's like co-contraction controls the volume of the stiffness ellipsoid. The posture controls the shape of the stiffness ellipsoid to very first approximation. So we call those common mode stiffness and configuration-dependent stiffness in some recent work that we have done with Arash. Okay. So now I move on, I talk about hands. That is connected. And one of the things that I believe natural machine motion is about is making simpler robots. More robust, more stable, more useful. So these are a few hands for robots that you see here. Hands for robots are something very interesting to many, I mean, to myself, since my undergrad thesis work, I'm doing hands. And these are beautiful hands that are around, have been around. Some of them are from the 70s, some of them are very recent. So there are many, many beautiful engineering pieces. It's a long history of hands. These are clips in 1989. In 1989, this is a JPL Stanford hand, or Salisbury hand also called. With this hand and a very simple intrinsic tactile sensor on the fingertip, a force torque based sensor, you could do things like measuring the friction coefficient on an object, sliding the fingertip, detecting different objects by the texture, by simply sliding the finger, having a reflex control of grasping, as you can see here, grasping an object with minimum necessary force, and then when the object tends to slip, you increase the force just to oppose the slippage, or do following and reconstructing the shape with tactile exploration. So these are things that are still now interesting, I think. They were done back in the 89. So why should we bother about robot hands? Aren't they a solved problem? There is a famous quote by Gil Pratt, the DARPA main person, who said grasping is solved. And that attracted the rage of all the community, because you cannot say that a problem is solved until people are working on that. But he was right. In some sense, he was right, because hands have been around that did things for a long time. So what's the problem with this hand? If you look at the back of this hand, there are at least a couple of problems. So the hand is nice and also almost same size as a human, roughly. But it has a big motor box here that was this big, connected to the hand by some Bowden cables, sheets and tendons, that were a source of friction and, most importantly, a source of very frequent breaks, especially at night, especially when you need them for a demo the next day, they would break a lot. So this is terrible. The real problem with hands is to make robots that are soft yet strong, simple and dexterous, intelligent, but also practical. So the approach that we followed is by merging two ideas. One is soft robotics, that is what you have been seeing here, and the other one is synergies, that I was referring quickly at the beginning. So I will tell you a little bit more about synergies now that are part of this natural machine motion idea. So the human hand is itself a very complex system. As you know, here are the veins, the arteries, the bones, the ligaments, the muscles, and these are the sheer numbers. You have 29 major joints. You have 123 ligaments, 34 muscles at least to move the hand. You have 48 nerves, you have an incredible number of tactile receptors, thousands, in the skin of the hand. How can the brain cope with that? I mean, how can the brain use the hand while he's thinking, while he's talking, while he's doing other things? There is some evidence in neuroscience that there exist what are called sometimes sensory motor synergies and constraints. So there is a long history of people that have been observing that muscles that, to put it the way that someone has it, the brain doesn't know about muscles. Yeah? So that means that, this is Bernstein, the brain doesn't really know about muscles. When the brain wants to do something, it doesn't talk to a muscle. It talks to a higher level of organization that is called synergy. So for instance, when we speak, just to get out of the realm of hands, when we speak, every phoneme that I say, if I say B, ba, I use at least 40 muscles to do this pa instead of B. And I use all the muscle in my tongue, cheek, mouth, lips, pharynx, down to the diaphragm. All of them are used in a very specific way to produce ba or p. It's incredible that the brain tells every muscle what to do at the exact same time, right? So this idea of synergy is that there is a higher level representation of the outcomes that you want from an action, and then the actuation is organized at a lower level so that all muscles that contribute to this phoneme will be called together and act together as a synergy. Now, that's the idea of synergies. In hands, there has been some interesting quantitative work that goes back 15 years ago. Santello, Flanders, and Söchting did a statistic analysis of humans doing grasp of different objects. These are called postural synergies. They took data from the hand, and that they did a covariance analysis of this data. So basically, you know what it is about. You take all the angles, you take the average out, and then you do the covariance. It turns out that the first two synergies in this sense are the principal vectors, the singular vectors. So the covariance matrix is a symmetric matrix, so you take a singular value decomposition, and then you take the first singular value, the most important, and you take the first singular vector that is associated to the singular value. Okay? So the first two singular values already explain 84% of the covariance of the whole matrix. The first three, 90%. If you use only the first vector, the first principal component, you already have more than 50% of the covariance of the whole. That means that basically you can replicate to 50% all grasps by using just the first, the simplest component. And a component is 1 degree of freedom. So in principle, you can have a hand that works half as good as the real hand that has only 1 degree of freedom. If you take it that, this is a bit rough a description, but I think it gives you the idea. So here is how the first synergy or first principal component looks like. This is the most frequent, statistically most frequently used combination of joint motions. And the second is this, and the third one is that one. Basically now, if you take these three and you combine, you do a linear combination of these three motions, you explain 90% of everything your hand can do. Meaning that things like these are probably possible, but are very improbable. They don't happen very much. So if you want to build a hand that is simple, you probably start with these degrees of freedom, right? So these are the degrees of freedom counted in a metric of importance. There are many ways you can count the degrees of freedom of a hand. You can say 1, 2, 3, 4, 5, 6, or you can say 1, 2, and so on and so forth. So human hands are, as I said before, those are human hands, but robot hands, what can we do about robot hands? So using this idea of synergies, you can do different things. First of all, this is a statistical analysis of how humans use their hand most frequently. So one application of this is to reconstruct the hand pose from measurements that are not perfect. So assume that you have a glove and you want to know the position of the hand. If you had a perfect glove, you just take the measurement, you know where the hand is. But gloves are not perfect, and especially if they are low cost, like a mass market glove or toy or entertainment, you have very few measurements, and not all joints will be instrumented and will be noisy. So one very simple idea is if you have these few measurements, only a few measurements with noise, how do you reconstruct the shape of the hand? Well, one thing you can do is do pseudo-inverse, right? You do the pseudo-inverse, you take the best minimum least squares approximation of the real position of the hand. This is a simulation of data reconstructed from pseudo-inverse from a real glove, and the real hand is very different from the reconstructed hand. Here is instead a minimum variance estimation that simply uses an a priori, that is the synergies. Meaning, I know that although my measurements are both compatible to this posture and these postures, perhaps, this is very unlikely. So I can take these away, I can discard this hypothesis because they a priori are against. So I simply do a minimum variance estimation. I use the synergies as a priori, the data from the person as a priori, and I project the new data on this a priori, and I find a more reasonable reconstruction. And then you can also ask the question that is more interesting to me. Okay, now I want to put I want to put sensors on my hand, and I only have a limited budget. I cannot measure everything. I only have so many sensors, and I have some accuracy. I cannot spend more for having more accurate sensors than this. So where do you put the sensors to have the best reconstruction of the hand? How do you spend your budget of accuracy and sensors for reconstructing the hand? Is it like every first joint, is it important? Or do I want to measure just the position of the fingertips? What is the most important part? So one question is that, okay, let's look at humans again. The human hand has a completely inhomogeneous distribution of sensing. The position of the hand is mainly sensed through skin stretch sensors. So to know where the joints are, we are not using any encoders, of course. We are not using any angular measurement. We are using skin stretch. Those are dominating sensors. And the skin stretch sensors are placed in the hand in a very non-homogeneous way. Question is there any relation between these and the shape of the hand? There might be a sense. If this is the first most common motion, perhaps what I want to measure is something that is related to this more than to something that is not very frequent. Therefore, you can design the sensing system optimally given the a priori from the synergies and place the sensor optimally. And indeed, if you do that, you have that the reconstruction is much better than if you do just a random placement or a uniform placement of sensors in the system. But now let me come to the final topic, that is design of hands, soft hands. We want to design hands, we want to design simple hands that can be used and also are robust. So first idea is, okay, let's use the synergies. In particular, let's focus on the first synergy. I want to build a hand that has that uses the simplest possible hand, one motor, So I would like the hand to move like the first synergy because it's the most likely for humans, right? So if I close the hand, a model of the human hand, according to the first synergy, here is the shape that I have in time. What happens if I grasp a hand? So this is a, seems to be a good idea. So I do a hand, I do some mechanism that closes the hand. Will that work? Not really. Why? Because if you close the hand according to the first synergy, the first shape, you will never grasp any object, not even the simplest, not even the sphere. You start closing the hand around the sphere, and then at some point you get with the first phalanx in contact with the object, right? No one else is in contact yet. You have the first contact. What happens after that? If you want the other fingers to get in touch, you have to penetrate with the first one. Because the shape of the hand, even though it's the first synergy, will not be consistent with the shape of the object, right? No one will guarantee that the shape of that object will be consistent with the shape of the hand. Okay? So how do you use the idea of synergies? The key point in grasping is how forces are applied and are controlled. So it's not just finding the position of the hand, it's to apply forces and control the forces that is important in grasping. And the geometric synergy model that I have been using so far cannot account for grasping force generation. So we are asking, what is the relation between grasping forces, postures, and synergies? And the solution is that humans are not rigid, and so shouldn't be machines. So if you introduce a model of compliance in the human, you have compliance that is due to contact compliance. You have some compliance that is due to the tendon system, to the muscle system, the capsule. So you have a compliance in the system that is here represented through this formula. So basically, you have some compliance at the fingertip, due in part to the object compliance himself, due in part to the fingertip compliance of your arm. And then you have some compliance at the joints or at the motors. So joint compliance is CQ, structural compliance at the contact is CS, CQ gets transformed through the Jacobian of the finger, you sum the compliances, then you invert, and you have the stiffness matrix of the grasp. So if you introduce compliance, then you can talk about forces. If you don't have compliance, you will have an hyperstatic system and a force indeterminate system, and you cannot really know what is going on with forces. So let's, since humans are not rigid, we introduce a model of compliance. And then you can talk about the internal force, the control of internal forces. Now, internal forces, maybe you do not know if you haven't been working in grasping hands, but internal forces are the crucial part of hand control and grasp control. Internal forces are those forces that a hand can apply on an object without moving the object. They're also called squeezing forces. When I have this glass in my hand, I can apply forces that will move the glass with the fingertips, but I can also apply forces that will not move the hand. Basically, I squeeze the object. Why do I do this? Because I want, for instance, to avoid that it goes down. If I don't squeeze the object will fall. So I have to increase the squeeze to increase the normal forces here so that I stay away from the limits of the friction cone. But not all internal forces are controllable, and only a part of the internal force are controllable. So internal forces are many. If you have many contacts like this, you have many contact points, and you have many internal forces. You have many possible combinations of forces that you can apply without moving the object, right? You can press this thumb against this phalanx or against this, and so on and so forth. All pairwise combination if you want. In grasping, we typically write a grasp matrix G that maps finger forces to object wrenches. So internal forces are the null space of this grasp matrix, all the finger forces that will not generate any object wrench. Now, this slide is a little bit technical. I'll be very happy to discuss this afterwards. But now I'll just focus on the main points here. So G is the Grass matrix. P, the kernel of G, is the space of internal forces. But internal forces, not all of them are independently controllable. Just to give you a sense of this problem is that you will never be able to control more independent forces than the number of motors that you have. You will agree with this, right? If you have a hand that has one single motor, you will not be able to control independent components of internal force that are more than one. Right? If you have two, it will be two. Right? So in a grasp like this, you have an internal force that the kernel will be 16 dimensional. So you cannot use all these forces. You have to use something less. And you have to exactly see what is this controllable internal space. So luckily, if you have a model of compliance, then it's a simple matter to find what are the actual internal forces that you can control with a given synergy model. And here is how it looks like. So what you can really control is this term here. It's a projector. It's a simple formula, actually, although it might not look like. So S is the synergy matrix. Every column of S is one of those principal components. So if you only use one singular, S will be a column. If you have two synergies, S will be two columns. And they are the principal components of the grasp covariance matrix. J is the hand Jacobian that sends joint velocities into fingertip Cartesian velocities, as usual. K is the stiffness matrix that we just saw before. And then you have this. This is a projector in the null space of G, the grasp matrix. The grasp matrix is the application that sends fingertip forces into object glances. And this projects in the null space according to the K-weighted norm. So it's simply pseudo-inverse weighted in K times G projected there, I minus that. So you can find this formula, and you can find a reasonable model of what you can control. What does it mean, basically? It means what we call soft synergy paradigm. That really is the merging of the ideas of soft robotics and synergies from neuroscience. So the idea is that the posture, the geometric synergy model, the principal component model, does not really dictate the shape of the hand directly. But it does rule an internal reference representation of the hand configuration. And then the higher level control of the hand commands this internal representation within the synergy manifold. The actuator system, the muscles, are controlled towards this reference hand. And the hand fingers and palm interact with an object, with the environment, through contact. And then the physical hand, the real hand, reaches an equilibrium between the attractor, which is this virtual hand that has the shape of the synergies, and the repulsion of the object forces. Okay, is that clear? I think I can show it. Again, the real compliant hand below is attracted by the internal reference but repelled by contact forces and reaches an equilibrium configuration. I think this video here explains it better. So you see the virtual hand is the wireframe hand. That is shaped according to the principal components, one principal component only. That shape is not compatible with the object. So it will go inside somehow. The real hand is attracted toward this mesh and is repelled by the object. As a consequence, you generate forces. Now, if you want to apply more force, what do? You move the reference inside, more inside. so it will squeeze more. The real hand will be more strongly attracted. Or you can keep the reference still, but you can change the stiffness. And therefore, you will have a stiffer grasp with the same delta position, so you will have a higher force with a stiffer grasp. So you have this possibility. Here is another example. You see the reference hand and the real hand coincide when there is no interaction with the environment because you have no repulsion. So the real hand follows the virtual hand until it gets in contact. When you get in contact, the virtual hand will go inside, and the real hand will be, forcing against the surface of the object. So here is the whole idea. That is the equilibrium hand, if you want. It's interesting, if you have had exposure to the work of Anatol Feldman, Bernstein school, the Russian school that is now mostly in the United States, of equilibrium point control and synergies. Most of these ideas come from that school in neuroscience. They have this equilibrium point model, and it really fits. It's called the lambda model by Feldman, the lambda muscle model. And I mean, this model fits perfectly, almost perfectly, because this delta sigma, they would call lambda. It's really the reference of the hand or the muscle system. They usually do that for the arm, not for the hand. The reference towards which you are attracted, and this is the stiffness that controls the force. Okay, from theory to practice, we started doing work on implementation. And again, you have to do things properly if you want to do a hand that is useful. So again, looking at how human fingers are built, Manuel, Giorgio, and others started designing a new hand based on completely new principles. For instance, here is the finger. The finger has no bearings, has no traditional joints, traditional kinematic pairs. Rather, it has phalanges that roll on top of each other, as you can see. And they are kept together by elastic ligaments that you can stretch. And if you can stretch them and let go, and they will go back in the right position, as you can see in these videos. And what is interesting is that you can, really bang it on a table, doesn't break. And this was completely different with the old times hand that I was showing before. They are very fragile. Here is the PISA IIT soft hand that is also on the NMMI initiative. It's a completely open source design. You can print it out. It's intended to be simple to use, low cost, effective, hopefully, and very low cost, I said already. That was the main, and very robust, yeah. So here is the hand that uses 18 anthropomorphic joints, but can adapt to many different objects. You can see this different shape of the hand with different objects. Only use one motor synergy, only one motor. If the hand closes without any object, it follows the first synergy, the first principal component observed in humans. But then, if an object is encountered, then it adapts to the object with this idea of soft robot. Now, there is an interesting point that I will not have time to deal with. That is, in this case, the hand is not really, it's not just soft, it's also adaptive. So there is one way of implementing adaptivity softness that is different from just having elasticity, and that is under actuation. So the hand uses under actuation, and of course, we will be happy to talk about this. But let me show the hand before. So grasping round and cubic objects of different shape. The hand is controlled in these robot experiments with a very simple command that is open, close. Or in some cases with a proportional, close more, close left. There is no basic intelligence in this task. You just go there and grab. And as you can see, the hand shapes different in different cases. I like this part. If you observe what happens here, the same hand, the same control structure, the same object, but two different poses. You look at the hand takes two different shapes. This is just passive. This is built in. So the hand shapes differently. In that case, it has a top grasp. In the second case, it has a pinch grasp on the handle. Right? So it's really something that is not coded. All the intelligence that you would think is there, because you see that it adapts to the task, is built in. And this is due to the fact that we are replicating the first synergy and we are doing it softly. So there are two different grasps depending on the affordance of the object. And I think this is what we call embodied intelligence. You can grasp handles. Can, of course, grasp bottles with different shapes, and then you can also do quick things, rather quick. That is not so impressive to you, but to me, I've been working on hands for many years, and that has always been, something I wanted to do. Just grab an object. And it was the first time I was very happy when it's safe and robust by design, so you can really mistreat the hand. Markus Grebenstein is an engineer in DLR in Germany, and he says that a hand has to do this in order to be of any use. If you can do this with another hand, it doesn't serve any purpose. So we were very happy to pass Grebenstein's test with the hand. You can really, throw it around. And then next thing was, okay, so we can do something with the hand. Let's try and let's see what humans can do. So we developed a very simple human interface at the beginning so that a human could have the hand here and control. Now, basically what you do with this device is you open and close the hand. You have a little lever within this hood, and the lever closes and opens the hand. And now you can wear the hand, and you can use it. We have an exemplar there, so after the end of the talk, you can play around, or today or tomorrow. So you see here Cristina Piazza, who is one of the authors. That was wonderful. She was undergrad when she did this work. She can do nice things with the hand. Actually, much nicer than what the robot could do. And then we went further. We took the hand to a fair. There were school kids that came and they played around with the hand. And we were so impressed because they could do things that we didn't even think they were possible. You can see the girl there is taking a coin from the... Now, this hand has one motor. We never thought it could do much. We thought that it could do, something useful, but it actually can do much more than what we originally thought. And then we started observing what the kids do. So the kids exploit softness, exploit compliance to shape the hand so that then the hand will be in the right shape to do something. And after looking at the kids, I started looking at my own hand. And if I grab this object, very often I do this. I use the environment and I use the object to shape my hand. I don't think so much about the position on the fingertip, but I do think about the interaction with the environment. Now, if you were doing grasping, these are more examples. Look at this. The hand only does this, but if you need to take a book out of the shelf, you can do that. So again, this is the human using the hand to do something. You only have one soft synergy, you have only one motor, but the shape depends on the object and the environment, how you approach the environment. Right? So you can do many, many things. Here is one more. You can grab a ream of paper. It's also heavy, but you can grasp it. And then it can be strong. can also be soft and take a single sheet of paper out of that. And again, you see the human is using the hand in an intelligent way. Here is Manuel doing some workshop work. I will cut this short because it's but this is interesting. This is, you know, it's not trivial to do. The first question I used to get with this hand was, okay, yes, you can do this, but can you press buttons? And the answer is yes. You can press buttons. Although, I mean, you don't have all the... Now, next is, can you play piano? No. We can't. But many other things you can do. Mainly because the hand is compliant. The hand is soft. And we know how to use it. We do it. Look at this. There is some dexterity you can have. Look, it opens deftly, opens the little notch, and then gropes, takes the object. Okay, so you will have time to try the hand if you want later on. Here are a few more things, like flicking, catching and throwing with the hand. Here is the manual. You have to give me, I don't have the real videos here, the latest one, you have to give them. But this is enough impressive. This is Manuel. Manuel is the only one who is allowed to do this with the hand because he is the father of the hand, so he can really mistreat it. So he's punching. This is 15 millimeters thick wood. And if you do that by your own hand, but forget my own hand. If Manuel does, Manuel is this big guy, so if Manuel does it with his own hand, it doesn't do it. I mean, it gets hurt. And the hand can do it. So questions. The human wearing this hand can do many things. Can we program a robot to use a soft, simple robot hand as effectively as a human? And then, using a simple, soft hands changes the grasp planning deeply. If you did study or work on grasp planning, I've been doing that for long years. So when you think of grasp planning, the issue is you have an object, you have a hand. Then typically you take your fingertips and you decide where should I put my fingertips to grab this object so that I have internal forces that are controllable and that can avoid slippage. How can I maximize the distance from the slippage risk? And minimizing the forces, that is the grasp quality index. There is a huge literature on that. Okay? So we have been focusing, we as a community, we have been focusing for many, many years on the details of where the pinky should be in order to make a good grasp. Now, this hand changes the things completely because you don't have all this degree of freedom. You cannot choose where to put the pinky or the index for what matters. What you can do is open or close. But, so planning is sort of trivializing in a sense. But you have freedoms to choose where you should put the hand initially with respect to the object and how you interact with the environment so that the shape of the hand is proper to do the task. Think of the mug, right? Your reasoning will not be about where to put the fingertips, but it will be, if I go from here, the hand will take the right shape. If I go from there, it will take the right shape. If I have... So it's a completely different paradigm to be studied. And I think this opens up a lot of new interaction. So if you give me 5 minutes, I will go very quickly towards prosthetic application using teleimpedance control on the hand. It's basically the same idea. We can control now the stiffness of the hand and see what happens. So let me skip all the details here. If the hand is too compliant, then you can apply forces, but the grasp will not be very robust. If you're too stiff, then a fragile object might break. You can use impedance to differentiate the grasp between soft and stiff objects. Like in this case, on the bottom there, you have a sponge. Let me show what you can do with impedance control of the hand. Yeah, so you can see here how you can adapt. For instance, this ball here is much heavier than it looks like. It has metal inside, so it's half a kilo, I think. So typically you start with a soft grasp, you miss, and then you increase more your stiffness, and then you grab. The hand now is controlled through EMG. So through the 2 EMG, you get the position and force control and stiffness control of the hand. Instead of using the lever, I forgot to mention this, we can use EMGs. So you control the hand without moving your hand, basically by controlling the muscles. And then you can also try and give feedback to the humans. The control of the hand is, when you see the hand, is very intuitive. As I said before, this tail impedance works magically well. But problem is when you don't see the hand. So if you are under the table, you don't see the object, you cannot control the force, you don't know what force is. If you see the hand, basically you have a visual capture that tells you much about the force. And actually there are videos, I think there later on, we will see videos where you can be very accurate in force control when you see the hand. But if it is below the table or somewhere else or in the dark, you don't see the hand, so what you can do? Then you need feedback to the humans. Of course, we have a simple hand. The hand is very simple. Again, it's completely open source. You can download, print it yourself, and it will cost you very little. It depends on how you cost your own time, but just parts are just a few thousands. It's not tens of thousands or hundreds of thousands like the shadow hand, for instance. It's an order of magnitude less, at least. But if you need sensing, you don't want to make a hand that is soft and cheap, very complex and fragile, because you add sensing and wires that will that will break very often. So again, you have to ask, what's the simplest sensing that I need to do the task? Turns out that there are very simple things that you can do. You can simply measure force by doing a torque observer, basically measuring the current and inverting the model to find the control. And then display this force through a simple cuff on your own arm. That means something that presses more or less, like the tool that you use for measuring your blood pressure, that will press more or less on the arm. So you have a feedback of the force. It's very simple, very effective. Other thing is, very useful thing is to measure the first contact when the fingers get in touch, which finger has touched first the object. If you want to acquire a grasp without seeing, what is really important is to find that, the ring finger has touched, then I move until the thumb finger has touched, then I can start grasping, right? So you want to know when the contact starts. And also you want to know if there is slippage. So both things turn out to be high-frequency signals. Because you have a contact that is a step, so it has a very strong high-frequency content, and slippage that has some very high-frequency contents in the fact that you have the texture that generates this high frequency. So it turns out that it's very useful to have accelerometers on the fingertips, not tactile sensors. We are not using tactile sensors. They are not so useful as accelerometers. And then replicate those accelerations, very high fidelity on the arm. So accelerometers, voice coils here, just like a stereo. You pick up vibrations from the hand, and you display with a voice coil on the arm. And just like stereo, It works if it's hi-fi, if it's high fidelity. If you do a lousy transposition of the sensed acceleration to the display, the acceleration, it doesn't work. If you do a good job, especially if you do analogic treatment of the signal, very accurate, then it works like magic. It's very convincing. It's like touching the object with your own hand. It's very important, the quality of the hi-fi system between acceleration measurements and display. So overall, you do these things, and you can do nice demos like these ones. Yeah, so you can grasp with the hand very accurately strawberries or noodles, dried noodles that are very fragile. Right? So you can do this very fine manipulation with the hand. This is a demo making coffee with the hand. This video was prepared by Arash Ajudani, who's now a postdoc. He did a PhD, comes from Iran. He's an excellent student. He's not as good at making coffee. So you'll see I object. I mean, I'm Italian, so I am very particular about making coffee. So it puts very little coffee, as you can see. It's not going to be good. Of course, you're using the true hand and not that one, mostly because the wrist is misplaced. So turning around is very inconvenient because it's not in the right position. So it would be like this, right? But if you had the hand in the right position, that would be okay. And this has application to prosthetics. Let me just quickly mention some of these. So we have started this project with the INAIL, that is the Italian government. You recognize this, the guy here, this prime minister in Italy, came to touch the hand. Let me go quickly here. So here is the very first experiments we did with the hand on an amputee. The hand has potential as a prosthesis because, for several reasons. It's very simple, robust, low cost. If the human controls it, has amazing dexterity, and it is very natural, moves naturally. It's natural machine motion. That's what makes the hand. Well, we are at the beginning of this. We are making the first patients. Giorgio knows much more than me about this. But the patients tend to like the hand much better than the classical prosthesis that you saw before. So classical prosthesis, here you see a few tasks. Like, for instance, taking a glass out of a pile of glasses, plastic glasses, not easy. You have to control the force. These are the standard. Yeah, standard prostheses are rigid. They're fragile, they're much more costly, and rigid. Some of them are very simple, still rigid. It's interesting that amputees tend to prefer the simplest prostheses to the most complex hands, because, of course, they're more robust. Here are some other videos. Should be there. Yeah. Yeah. And here you see some fine operations made with the hand on the processes. Again, this is a good case for making a hand that is anthropomorphic, of course. Preparing a tabletop, manipulating glasses. As I said before, look at that. You have to keep the glass, but you don't have to squeeze too much. Yeah. Let me just finish with this. pretty happy, satisfied. Okay, so finally, bio-awareness means knowing biology and applying to robotics, not copycatting, but moving from nature to an abstraction layer and then applying to a different body. So trying to understand. Maths, control, modeling are important. Embodied intelligence, there can be a mind without a body. Build a science of embodied intelligence, abstract the insight from nature in terms of mathematical models, and then apply this new theory. And I like this, Galileo, of course, is from the same city as we come from. The universe is a book which cannot be understood if one does not learn the language and the symbols in which it is written. And these are triangles, circles, and other geometric figures without which means man cannot understand a single word in that book. And without these, it is just wandering in vain in an obscure labyrinth. So this is the group of people that did all the work that I've been reporting to you. So this is it. It's a bit late. If you have questions, urgent questions, I can take them. Otherwise, we can talk over lunch or afterwards. No questions is more urgent than lunch, so we can go. Thank you.
Thanks. See you.